to the session about C. The C language is the de facto standard for embedded systems due to its widespread application and fast execution. In this course, we will not start with the basics of C, and we assume that you are already familiar with the language. If you are an expert, feel free to skip the session. If you are not or not sure, let's dig in and let me tell you what the session is all about. In the next few video lectures, we are going to talk about the basic types and what commands are available to control the flow. Then we will continue with data structures, pointers, and call by value and reference. Later, we briefly show some specialties of C programs in the domain of embedded systems. Are you ready? Let's get started with the basic types. Here is a table of some of the basic types in C. Not all of them are basic types, but derivatives such as the bool value. In fact, bool does not exist in C. However, due to its usefulness, the Arduino and AVR libraries are defining it for the convenience. Since we are talking about basic types, I would like to take the opportunity and clear a misconception here. It is assumed that Boolean has two states, namely true and false. Hence, it is believed that bool is only 1 bit wide. However, this is incorrect. It is 1 byte. Therefore, changing a variable type from, for instance, character to bool does not reduce the memory footprint at all. In C, any value that is not equal to 0 is considered to be true. Later in the lecture, I will demonstrate how you get variables that are only 1 bit wide at minimum. However, if you do not use the other bits of the byte, then they are wasted, since the so-called word width is 1 byte in the Atmega MCU. Okay, what else do we have? Also for your convenience, types such as int8, int16 and so on, with a sign and without it are defined. The number in those types indicates how many bits they have and hence what the ranges are. So int8 is an 8-bit wide signed integer and therefore ranges from -128 to 127. Interestingly, on contrary to the integer type used in PCs, here an integer is only 2 bytes long. If you want to use a 4-byte long integer, you have to use the type long. Also in Arduino, the pointer type is only 2 bytes long, which is sufficient to access the entire memory space available. After starting with some basic types, what do we have to control the flow within a program? First of all, we have the famous if-else branches. Here, we see that the developer defined two characters of 1 byte each. A is set to 1 and B equals 4. Since C considers any value not equal to 0 to be true, the if condition in line 2 will return true and the if branch is going to be executed. In line 8, a similar if condition is implemented. However, the operation is quite different. It is a bitwise AND. Observe that compared to the logical AND in line 2, 1 ampersand is missing here. Hence, this translates into a bitwise AND of 1 and 4, which results in 0, and therefore the if condition is false. Therefore, in this case, the else branch is executed. It is always a good idea to check the conditions and distinguish the logical and bitwise operators, since both have their own distinct purpose. We also have several instructions to create loops, such as for, while, and do-while loops. All loops shown in this listing will iterate 10 times. After the first for loop completes, I will be set to 10. Keep in mind that while I is not equal to 0 and hence false, the second while loop will continue to execute. Important is that you do not forget the semicolon at the end of the do-while block here. And we have functions. Every program needs to have the main function as an entry point to start the program execution, but it allows also user-defined functions. Functions reduce code duplication and make the source code more readable. For instance, the commands to read a particular sensor can be integrated into the main multiple times. However, if the developer decides to insert them into a function called readSensor, another developer automatically knows that this function reads the sensor without the necessity to understand how the function works. In addition, if there's a bug in the function, it needs to be fixed at only one place in the source code, and all function calls become fixed. Great, that means less work and less error prone. Later we see that the compiler is able to recognize and remove unused functions from the binary as an optimization step. Hence, it is a very good idea to utilize this functionality, may it be for recursive functions or iterative function calls. Usually, a function call is quite costly in terms of saving the state on the stack, issuing the call instructions to the function, returning from there, and restoring the state. Hence, to avoid this overhead, small functions might be inlined by the compiler as another optimization step. That is, in the final executable, the function call is replaced by the actual function body instead of the call. This is at the discretion of the compiler, while the source code still remains the same. That's all about the control flow structures. Obviously, it's just a brief overview to jump your memory. If it is all new, what we discussed so far, we highly recommend to take a beginner's course about C. There are plenty of free tutorials and courses available. Once you understood the underlying concepts, please come back to this course to complete it. We promise, once we handle the theory, this course becomes very practical and beneficial. In this session, we will talk about data structures. Ready? Let's dive in. Let's start with one of the simplest and most useful data structures, the array. Basically, it is a variable able to hold multiple values. Your shopping list, for example, contains multiple groceries that you would like to buy. So the array shopping list contains milk, oranges, coffee beans, and so on. Or, in our example, we just have an array with 5 integers, 1, 2, 3, 4, and 5. In the memory, the array is a sequence of the values consecutively stored in RAM. Here, the first element, the integer 1, is stored at address 200 in hexadecimal format. At the next memory location, the 2 is stored. But why does the memory address increment by 2 here in this example? Well, remember that an integer is 2 bytes in total, and this memory stores 1 byte per address as indicated by the LSB of 0 and the MSB of 7. Hence, the memory's so-called word size is 1 byte. That means storing an integer requires 2 memory locations. If the maximum value is less than 255, it would be a lot more beneficial and memory efficient if instead of type int, uint8 or int8 is used, considering that currently the upper byte of the array elements is always 0 anyway. Let's do that. See, we need only half the memory space now, and the last element of A is stored at address 204 instead of 208 earlier. Let's do some exercise. That is the most interesting part of the session. What will be printed on the terminal for the size of the array? Since it has 5 values, 1 byte long each, 5 and 1 will be printed respectively. Let's have a look at line 7. Here, the hexadecimal pointer value indicated by the %p of A is printed. What is the value of A? It is the address of the first element, and hence printf is going to print that address. Therefore, 200 is being printed. What if we would like to print the value that is stored at this address? Add an index to A. Here, the address is taken and so-called dereferenced, which means that the value stored at the memory address is returned. Hence, the printf in line 8 prints 1. What happens here? Well, we take the A and use the star, which is a dereference operator. Again, so we check what is the value stored at the address 200. Hence, again, a 1 is printed. Oh, something more interesting. We take the address of A, which is 200, and increment it. Hence, we get the address 201. And then we dereference it. That means we check the value at address 201 this time. And what is that? Oh, right, it is 2. Easy, right? Let's move on. Here we use the ampersand in front of A. That means take A and return the address of A. A is currently an address pointing to the first element in the array. So what will be printed? Right, 200. It is the same value that is also printed in line 7. Well, that is interesting. And in a minute we will see what different methods we have to access the pointers and the values. Here we see the ampersand in front of S1. Since the ampersand is the address of operator, this instruction will return 205. That is the memory address in which the value of S1 is stored. Okay, that is quite a bit. We saw that there are multiple methods to access the array elements and the pointers. What are those methods? Let's summarize them. And here they are. First, we start with the values which are stored on the right side. To access the first element in an array, we can use the dereferencing of the pointer, that is the star, or alternatively an index. The type in both cases will be the type that is stored in those memory cells. In our case, it is unsigned integer of 8-bit. To access the second value, we just increment the pointer by 1 and dereference it, which is mentioned here, or alternatively, we increment the index. That is the simple part. Let's have a look at the pointers, which are mentioned here on this side. Well, A points to the first element in its array. So we can add 0 to the pointer, essentially not doing anything. It still points to the same element. We can also take the value of the first element and ask for the address of it by using the ampersand or the address of operator. In all cases so far, the type is a pointer to the uint8 value stored at this memory location, which is mentioned here. But what if we use the address of operator on A itself? It still points to the same memory location of the first element, so its value is still 200. But there is a difference, and that is its type. It is of type pointer to in total 5 unsigned int8 values, which is the entire size of our array. Same with if we take the address of A and add 0 to it, which does not do anything. Why is that so, and what's the difference? Let's take A, which is 200 and of type pointer, to a unsigned int8 value and increment it. Hence, we have the address of 201 of the same type, a pointer to a unsigned int8 value. In contrast, let's take the address of A using the ampersand operator. The returned value is again 200. Since its type is a pointer to 5 unsigned int8 values in total, incrementing it will not result in an address of 201, but in an address of 205. It jumps over the entire array due to its type. This is very useful, and you already applied it without thinking about it. Going back to the unoptimized version of our program earlier, in which integer was used to store the elements of our array. If we say a plus 1, we would like to have a pointer to the memory location of the next element and not the next address. So in this case, a plus 1 will result in an address of 202 and not 201, pointing to half of the first element. That is why the type is important, and it is very convenient, isn't it? As a summary, a star is a dereference operator, which means go to the address and get the value stored there, while the ampersand is the address of operator. It's simple, right? It takes a bit of getting used to it, but it's not that difficult. If you try it on your PC and you get segmentation faults, that means that the operating system terminated your program because you accessed memory you are not supposed to. In embedded systems without an operating system, you are free to access and mess up everything. Oh, by the way, the addresses that are used here are for demonstration purposes only. Your memory organization might look very different. Let's have a break here and do some exercises. I know it was a bit fast, but through exercises it should become clear. Only practice creates masters. So head over, do them, and come back for another lecture about data structures. We will stop with pointers here for now. Welcome back from the exercises. Now you probably have a better idea how pointers work in C. Let's continue with other data structures C has to offer. One of them is the enum type. On the left, a developer decided to use hash defines, which is fine. Despite the intention to have only red suits, that is hearts and diamonds, available, the suit S can be assigned any value between 0 and 255 since it is an unsigned character. An alternative is to define suit to be of type enum, but even enum is internally organized as an integer, and therefore every enum item is represented by a number. Therefore, even integers outside of enum can be assigned to S. Here, 5 in line 11. You don't believe me? Well, head over and try it for yourself. The additional n in the enum type is a little trick, so we can easily check how many entries are available in our enum type. So this loop prints out 0 and 1. Since diamonds is represented internally as 0, hearts as 1, and n as 2. That is a little trick, the n. So no matter how many elements the developer inserts, n is always the maximum, and hence the loop works. For instance, the developer decides to include the black suits as well. Nothing needs to change except the enum type. N automatically becomes 4. It saves time and prevents bugs, as the developer does not have to scan through the code checking for boundaries, a mistake that happens quite often, as we will see in a later lecture. Is that all? No, we have more data structures. One of the most underestimated data structure is union. It is similar to struct, which we will have in a bit. However, instead of reserving memory for each of the elements in the union, the elements are overlapping. Since an integer is 2 bytes and we have 2 characters in an array, the entire union is 2 bytes in size. Does that make any sense? If I write to C0, it will change the integer as well. And if I write to the integer, it will change the character array. That's crazy, isn't it? Well, not always. There are situations in which you will need only the higher byte of the integer, for instance. Instead of extracting it by shifting the bits around, you will be able to get it by accessing C1. Isn't that elegant? That brings us to the last data structure in this lecture, the long-awaited struct. It is declared like the union earlier. However, every element has its own dedicated memory space. So writing to the integer in the struct number does not affect the array C. If we print the value that is stored at C1, we just do not know what that is at the moment. Okay, that's all for now. In the next lesson, we are going to talk about the last chapter for the session, the call by value and call by reference. Basically, there are two ways how parameters are given to a function. Depending on the chosen technique, it is either a call by value or a call by reference. Let's handle the call by value first. Here we see a function called func and it has a parameter. The parameter is expected to be a struct. It is accessible from within the function by the variable name ns. So what happens here when the CPU starts to execute the main and comes to the function call inline 13? Well, let's start from the top. First, we reserve memory space to hold the struct. Remember, we need 4 bytes for that. Then we access the integer within the struct and set it to 5. For that, we load 5 into a register and then store the value into the memory location of I in the struct n. So far, nothing spectacular happened. Now we reach the function call. Since the function call expects a struct as parameter, we give it our struct number. That means that the entire struct is copied onto the stack. So basically in the memory we have 2 structs with identical values now. One is in normal memory, accessible through n. The other one is on the stack, accessible within the function using ns. We also push the program counter onto the stack so that we know where to continue once we've finished executing the function. But that would be another topic for another lecture. Let's continue. What happens next? The CPU calls the function, which means it jumps to the first instruction in the function where we want to increment the value of I. Since only the struct ns is available within the function, n is only available in the main, we manipulate only one version of the struct. Then the integer of ns is printed. So it is copied onto the stack before printf is called. After that, we return to the main, discarding the stack and hence the struct ns. As you can see, we never even touched the struct n, and hence its value is still the same, and 5 is printed last. Now we are facing 2 questions. First, what shall we do if the function has to manipulate the integer and we want to make the changes also available in the main? And 2, what is the disadvantage of call by value? Before continuing and answering the questions, let's divert for a moment and have a look how the compiler could optimize our program. The compiler has a look what we want to do. We never touch the character in the struct, so why shall the compiler keep it when we do not use it? So very likely the compiler got rid of that array. Okay, a constant of 5 is assigned to the integer in the struct. What else do we do with that integer? Well, it is copied to the stack and the function is called. In this function, a 1 is added, it is printed and then discarded. So why do we even call the function? It can be inlined. In addition, the program shows exactly the same behavior if first a 6 is printed and followed by a 5. The compiler sees that and reduces our program to 2 calls to printf. By doing so, we get a smaller and faster program. Not possible? The C compiler has seen decades of development and its optimization routines became very smart. Implement this program, interrupt the flow of the GNU compiler collection after the compiler, and have a look at what it produced. Especially use optimization flags such as O2 or OS, which we handle in the next chapter. But back to our questions. How to manipulate values and make those changes available outside of the function, and what is the disadvantage of call by value? The latter question is quite easy to answer. Imagine a very large data structure. It will take quite a bit of time and stack memory to copy the entire structure. You might run out of memory. And to what extent? To discard it in the end. Hence, keep the structure small, copy only those values that are needed, or trust the compiler that it selects the values for you, which it does. However, if optimization fails or you really need all values, consider a call by reference instead. That we are going to handle next. Here we see an example for a call by reference. On the first look, not much has changed. We added a star to the function parameter right here. Since it is in a declaration, it is not a dereference operator, but it indicates that the parameter is not the structure, but an address whose value points to a structure. We also replaced the access operator for the elements by an arrow, here and in this line. This is a short form of a dereference operator. To increment the integer, we first need to have a look which memory address NR points at. Dereference it to get the value of the memory address, which is a struct. Then we require access to the integer. Instead of the arrow, we could have dereferenced NR using the star and then the dot operator, as in the previous call by value example. The arrow is an elegant short form to implement the same. What else has changed? In line 13, we added the ampersand here. Recall that this operator says we need to get the address of n. So now we are all set. Let's run the program. Again, we set the integer inside the struct to 5. But now we give the address of the structure to the function func. Hence, only that address is copied onto the stack. Remember, addresses are only 2 bytes long, so we do not copy the entire structure here. Inside the function, the integer is accessed by dereferencing the address of nr, which equals the address to n. Since we do not work on copies of structures like before, and if something changes in that structure, the old value is overwritten permanently. So we increment the integer and have to store it back before printing the new value of 6. Then we return to the main. We discard the address that we pushed to the stack earlier and not the structure itself, and continue with the instructions in the main. In the main, the integer is accessed again and printed. However, since we manipulated the memory location of the integer and not a copy of it, 6 is printed here as well. Okay, that's all about call by value and reference so far. Let's finish this session by briefly pointing out some differences between embedded systems and your PC. First, many times embedded systems don't have an operating system which protects memory spaces from curious memory dumps, running multiple programs seemingly simultaneously, etc. So what shall happen once a program ends? The CPU is still powered and clocked. That means even after your program ended, it will still do something. What it is, we will not know. Maybe it will execute instructions that are still there in the memory till it reaches the end of the memory and then restarts from the beginning. To prevent this undesired behavior of unknown states, the program always contains an endless loop, such as a while one, which is always true. A program is also difficult to debug. Many times you do not have a screen and rely on text sent through the debugging serial interface. However, inserting plenty of printfs might alter the timings in your program. It might happen that now protocol timings are violated because the CPU becomes busy printing your debug information. In embedded systems, other keywords become more important, such as a more fine-grained data type declaration like int8, int16, int32, and so on. Also, the keyword volatile receives more attention. That keyword we will discuss in a chapter about interrupts later in the course. Often, the entire memory is addressable and accessible. That not only includes the RAM in the processor, but also the CPU registers or registers controlling the pins, for example. So the developer can exactly determine when and how the pin has power or not by writing values to specific addresses. That means that one address might alter the state of the pins, while another points to the value stored in the RAM. More about how that works in the next lecture, which will be very exciting. The last difference that I would like to point out is that for PCs the memory is essentially limitless for the small programs that we write. So we concentrate more on speed and tell the GNU compiler collection to optimize our code for fast execution times and not so much for memory usage in terms of RAM and binary size. However, in embedded systems, speed is secondary. In fact, they just have a few megahertz of clock speed, which is magnitude slower than your PC whose CPU sleeps at, for instance, 800 megahertz, a range that is out of reach for most embedded systems. Hence, while we have enough patience for computation, we have limited memory space. So the priority shifts from fast execution times to ask the compiler to make the binary smaller, using maybe less instructions that are eventually slower in execution. In fact, the Arduino Uno that we are going to use in this course has only 32 kilobytes of program memory. That is equivalent to a few pages of text. In fact, every second of this video requires around 320 kilobytes of storage, which is 10-fold more than would fit into the Arduino Uno. So it is incredibly small, but still powerful, and we see later in the course that we can do amazing stuff with even less than 32 kilobytes. That brings us to the end of the session, in which we discussed quite a bit. We started off with some basic types and their ranges and worked our way up to data structures such as structs, unions, and arrays. On the way, we had a look into pointers, and we ended the session with practical examples for a call by value and reference. What we will do next is diving deeper into registers, how to access them, and how your embedded system communicates with the real and physical world surrounding us. We require a working knowledge of pointers here because we are going to use them. Therefore, if you are new to C, I highly recommend doing the exercises before continuing. Thanks for watching, stay tuned, and see you in the next chapter.